In this video, we continue our study of triple integrals, and we will start by reviewing how we represent the volume of a solid region Q with a triple integral. We'll review a formula for the mass of Q, and then we'll talk about cylindrical coordinates and why we might want to integrate in cylindrical coordinates as opposed to rectangular coordinates. And we'll do a couple of examples. So let's consider a surface, or actually a solid, Q. So it's in three-dimensional space, and maybe the upper bound of Q is some function that looks like this, given by z equals f of x, y. And maybe the lower bound of Q is a different function. It looks something like this. We'll say that that's g of x, y. And Q is the solid region in between. So it's not the boundary. It's not this surface joined with this surface. It's that whole solid. If we want to find the volume of Q, we generally do two things. We think of z as going from a top function to a bottom function, or from a bottom function to a top function. And then we look at the projection of Q onto the xy plane. So maybe z equals f of xy and z equals g of xy meets along a curve, meets along this curve right here that you see in the picture. When we look at the projection of that onto the xy plane, maybe it looks like this. So that curve where they meet, that forms that boundary. And then we know just from the picture that the region R of integration is the interior of that region. Or that's where the region of integration would be if this were a double integral representing the volume of the solid Q. So if I want the volume of Q, basically I've got to do two things. I've got to think about what the top function and bottom function are here. Z goes from a bottom function to a top function. And then we have to look at the projection of the solid region Q onto the xy plane. The way I always like to think of it is it's as if the sun were right here. And because the sun is right above the positive z-axis, the sun is casting a shadow from the solid onto the xy plane. And it's not at any angle. It looks like it's at an angle, but it's directly above, so that we're seeing we're seeing what we would get if we projected onto the xy plane and there was no z dimension at all. That's R. You have to describe R using the methods that we discussed for describing R before. So you can let x go from a function to a function and let y go from a constant to a constant, or the other way around. You can also describe R in polar coordinates if R happens to be a circular region or part of a circle. So we'll talk about that in a little bit. So let's say we want the volume of Q. It's generally represented this way. It's the triple integral over Q of dv. And that dv can be split into two pieces. This is how I tend to think of it anyway. I usually let z go from a bottom function to a top function. We do that integral first. The antiderivative of 1 with respect to z is z, and then we would evaluate at f of xy minus g of xy, or at f of xy and g of xy, and subtract, and so we'd get f of xy minus g of xy, top function minus bottom function, and then we're integrating that over the region R. And the region R can be described two different ways, but let's say that y went from a function to a function, and x goes from a constant to a constant, just for example. Then y would go from some function of x to some function of x, and x would go from a constant to a constant. Now there are other possibilities. X could go from a function to a function and y could go from a constant to a constant. We don't have to integrate with respect to z first, although I tend to think of it this way. But yeah, this is one possible order of integration. And the way I'm thinking of this is I'm thinking of this as these innermost bounds represent the bottom function to the top function for z. When I say bottom function, that just means smaller z values. And then I look at the projection of my region onto the xy plane. I've got that solid region Q, and maybe the region R looks like this in the xy plane. And then this you can describe however you like. You can let x go from a function to a function and y go from a constant to a constant, or the other way around. And if neither one of those work, sometimes you've got to do a combination of those. Sometimes you've got to add several integrals in order to let y go from a function to a function. Maybe y goes from a function to a function on one interval, and it goes from a different function to a different function on another interval for x. But then your bounds for x and y, these are just bounds that describe the region R. Okay. So that's one way to think about it. One way to get the volume of Q is this way. So I let z go from this bottom function to top function, and then we project onto the xy plane. Notice I'm letting z go from a function to a function, and then I'm projecting onto the plane whose variables do not contain z. I'm projecting onto z equals 0, basically. So I'm projecting onto the xy plane. That's one possibility. And there are two other possibilities, but I guess this is actually one or two possibilities depending on how you look at it. Z goes from a function to a function, and then you project onto the xy plane, and then you've got two different ways you can orient this. So this would lead to a dz dy dx integral, or you could do dz dx dy, depending on how you described R. So that's one possibility. Another possibility is maybe your functions look like this. Maybe y goes from some function of x and z to a different function of x and z. So maybe this is y equals some function of x and z, and this is some function of x and z over here. In this case, if this was my solid region Q, the way I would want to handle this is I would want to say the volume of Q is the triple integral over Q of dv, that's dx dy dz, or you can change the order because multiplication is commutative, that's all fine. But since y is going from a smaller function to a larger function, in this case it's going from a left function to a right function, I might want to integrate with respect to y first. So I'll let y go from that left function to the right function. Notice that these depend on x and z. So then we integrate that with respect to y, and we get these bounds. And then we'll look at the projection, but this dA and this R are different than that R. This is a projection onto the xz plane. That dA is dz dx or dx dz, whichever you prefer. So in this case, y goes from a left function to a right function. And then we look at the projection onto the xz plane. And maybe the projection onto the xz plane, it's a little bit hard to draw, looks something like this. So here's z, and because we're in a right-handed coordinate system, rather than putting my x-axis over here, I'll put it over here. So it's like I took this xy, or this xz plane that I see, and I'm just rotating it this way, okay? Or actually, I'm taking something that looks like this, and I'm rotating it that way. So there's my xz plane. Then maybe my region R looks like this in the xz plane. Now you've got choices for that one as well. Z can go from a function of x to a function of x, and and x can go from a constant to a constant, or vice versa. But these are bounds that describe that region R. But notice that the projection this time is onto the xz plane because I let y go from a function to start. So y went from this left function to right function, and then we project onto the xz plane. So that's one way to represent volume. Okay. So we let z go from a function to a function and project onto the xy plane, or we let y go from a function to a function and we project onto the xz plane. Can you guess the third way that we'll represent this? This is what we did in the examples at the end of the last video. This is hard to draw. They're all hard to draw, aren't they? Maybe I've got some function over here. This is particularly bad. Okay. That's not a very good picture. No, that's really horrible. I'm going to try again. So I'm imagining some function back here, and then there's another function up here. Yeah, that's really bad again. I'm so sorry. That's okay. So this time I want x to go from a function of x and y, or function of y and z, excuse me, to a different function of y and z. It's x. Why can't I write right now? Okay, so this would be a back function and a front function. You see why it's so hard to draw. I should have visualized it. I should have looked at some graphs first and then tried to copy what I saw, but tried to do it completely in my head, and that's what we get. But we want to go from smaller x values to larger x values, and remember, larger x values are closer to us, and the way this right-handed coordinate system is drawn. So my x could go from a back function to a front function. And those functions could be functions of y and z. In that case, the volume integral, the triple integral over q of dv, can be written this way. We let x go from the smaller x values, which is given by the back function, to the larger x values, which are given by the front function. And then we're going to project again, but this time dA is not dx dy. You've already taken care of dx. This is dy dz or dz dy, either one. So you're going to project onto the yz plane. I don't know what it will look like. But here's z, here's y. You project onto the yz plane, and then those form the bounds for y and z. And of course, y can go from a function of z to a function of z, and z can go from a constant to a constant, or the other way around. So those are your 3 options, but they really correspond to 6 options for evaluating a triple integral representing volume. And even if the triple integral doesn't represent volume, if you've got an integrand other than 1, if you're integrating some function over a volume, so you're multiplying a function by all these little volume pieces, like a weighted average, this is how you'll get your bounds. So you've got a couple of possibilities. You could integrate with respect to z first. So z goes from a bottom function to a top function. And then we describe our projection onto the xy plane as a dy dx projection, I guess. Or we could do dx dy. So this variable goes from a constant to a constant, the one on the outside, and this one goes from a function of this variable to a function of that variable. Or we said y could go from a left function to a right function, and then we could integrate with respect to z and then x, or x and then z. So here we look at the projection onto the xy plane, or excuse me, the xz plane. Oops, I wrote XYZ plane. No, just XZ. Or the third possibility is we could let x go from a back function to a front function, and then we could integrate with respect to y and then z, or z and then y. But here, then we would project onto the YZ plane. So those are your options. I tend to stick to this one most of the time because it's easiest. It's the way I think. I think of z as going from a bottom function to a top function and then a projection onto the xy plane. But sometimes it's necessary to change the orientation, change the way I'm thinking about it, so that I can set up the integral. And sometimes maybe the integrand is written in such a way that I want to integrate with respect to a different variable first. So I would switch in that case. Okay, so that was our review of triple integrals representing volume. Now, I also said we would review the mass of a region Q given a density. So if I know the density of my region Q, maybe density is given by rho of x, y, z, and this is mass per unit volume. And when I write density as a function of x, y, and z, all I'm saying is that the density varies. At all the different points in the solid region Q, I've got a different density. There might be some points that are more dense than others. And this is a function that's representing that. If I want the mass of this, well, I would break my solid region Q into a bunch of little cubes, and to find the mass of that one little cube, let's say we're looking at the ith, jth, kth cube, in the ith subdivision in the x direction, jth subdivision in the y direction, kth subdivision in the z direction, then mass is going to be the density at x sub I, y sub j, z sub k. So it's the density at a particular point chosen within that cube times delta v, where delta v is delta x times delta y times delta z. Because I'm taking mass per unit volume and I'm multiplying by volume, and then I'm getting a little tiny mass. And then I want to add all of those together in the x direction, the y direction, and the z direction. And that gives us a triple integral over Q of some function of x, y, and z. and that represents mass. Okay, now, so we've reviewed the ideas, the main ideas. Now let's talk about cylindrical coordinates. Cylindrical coordinates are just another coordinate system, like rectangular coordinates, but these are cylindrical coordinates are a way of describing triple integrals. So it represents, these are coordinates representing x, y, and z, like 3 spatial variables. But instead of representing points as x, y, and z, we're going to convert from x, y, and z to r, theta, and z. And this is really not that difficult at all because we've already studied polar coordinates. Cylindrical coordinates are just basically polar coordinates, and then you just add the z on. And so you just let z equal z, and you change all of your x's and y's to the corresponding r's and thetas. So remember our polar coordinate conversion formulas. X is r cosine of theta, y is r sine of theta, x squared plus y squared is r squared, and tangent of theta is y over x. If we look at our picture, that's r, that's theta, that's x, that's y. So this point can be represented uniquely as xy. This one's not unique, but another way to represent it is r comma theta. And so that's polar coordinates. In cylindrical coordinates, we're taking these polar coordinate conversion formulas and we're adding one more formula. It's just z equals z. You might be saying to yourself, well, what does that mean? Well, instead of taking our solid region Q, and splitting it into a bunch of little cubes with volume dV, or volume delta V, which is delta x times delta y times delta z. We're going to represent volume differently. It's going to look more like we took polar coordinates and then we superimposed this z dimension. So in the xy plane, you've got all these circles. That's r equals 1, r equals 2, r equals 3. And theta equals 0 is on the x-axis, and then theta increases through all these different values. And you get a grid like that in the xy plane. I try my best to sketch this. This is where I wish I was a better artist. My dad is an artist and my little sister is an artist, and I respect what they do so much. Okay, that was my attempt at a little piece in polar coordinates. Actually, or cylindrical coordinates, excuse me. Let's look at an area piece in polar coordinates. Having trouble with my polar grids today. Okay. So the area of this little piece in polar coordinates, we said, was r times dr d theta. The farther we get from the origin, the larger that piece becomes. So it makes sense that it's proportional to that distance from the origin. But it's also multiplied by the change in r and the change in theta. And so we get this identity. dA is equal to this. Or if you prefer, you could do this. Delta A is delta r times delta theta, and r star is just the average r value, the r value between this r value and that r value is r star. In cylindrical coordinates, the area of that bottom piece is still delta A, where delta A is given by this. And then we're just going to add a third dimension, delta Z. So delta V is delta Z times delta A, or delta Z times R star delta R times delta theta. Or in other words, our dV is just going to be R, dr, d theta, dz. And of course, we can multiply in different orders if we want to. But the idea here is, basically you're doing, you've got a triple integral. If you are evaluating a triple integral and you project onto the xy plane and you see a circle, and you're like, man, I wish I was in polar coordinates. Well, you can change to polar coordinates. You can change to polar coordinates before all that starts, but we don't call it polar coordinates. If there are z's involved, we call it cylindrical coordinates. So let's talk about why we might do that. If the region that you're integrating over you write this down first. Use cylindrical coordinates when whenever the region that you're integrating over has symmetry about a line. Kind of like a cylinder exhibits symmetry about a line. You might want to be in cylindrical coordinates. You might use cylindrical coordinates when the integrand involves x squared plus y squared, or tangent, or y over x, excuse me. Because if the integrand involves x squared plus y squared, or y over x can be replaced by the tangent of theta, and x squared plus y squared can be replaced with r squared. So we might want to go to cylindrical coordinates if we can simplify the integrand by using our cylindrical coordinates formulas. Lastly, if the projection onto the xy plane is a part of a circle, we call that a circular sector, then we might want to go to cylindrical coordinates. But from the big picture, or in the big picture, like what are we doing? Why are we doing this? These are details. If I see one of these details, I know I want to switch to cylindrical coordinates. But if you're saying to yourself, what's the point? We're changing to cylindrical coordinates when it makes evaluating the integral easier. So we want to use cylindrical coordinates when it's easier to evaluate the triple integral in cylindrical coordinates. I know that there's probably a much better way, a more efficient way to say that, but I didn't think of it when I was writing it down, sorry. So we want to use cylindrical coordinates when it'll be easier, and when will it be easier? It'll be easier if using cylindrical coordinates simplifies the integrand. So we use cylindrical coordinates to do one of two things. We use cylindrical coordinates to simplify the integrand, or to simplify the description of the solid region of integration. So we're trying to either simplify the integrand or simplify the bounds. If we have symmetry about a line, if the projection onto the xy plane is part of a circle, if the integrand involves an x squared plus y squared or a y over x. Changing to cylindrical coordinates might make the integrand simpler. It might make the description of the solid region Q simpler, might make our bound simpler. And so we would want to switch in that case. Just like when we used polar coordinates, I would stick to rectangular coordinates, which are more comfortable for me, as long as it makes sense to stay in rectangular coordinates. If the region looks like part of a rectangle or something that's easily described in rectangular coordinates, we want to stay there. But if the region is much more easily described in terms of r and theta, I would switch to polar. The same thing is true here. We're just calling it cylindrical coordinates because we're adding a z. And whenever we look at our little pieces, the delta A in the xy plane is a little tiny area piece, and it looks like on polar plotting paper, a little area piece like that. We're just going to add that third dimension delta z to get a new delta v. So it's just RD theta times dz when we move to cylindrical coordinates. So let's do a couple of examples. Let's just say we want to find the volume of the ellipsoid given by 9x squared plus 9y squared plus z squared equals 36. Well, the first thing that I would do in order to set up the volume integral is graph this thing. And in order to graph it, it would be best if I wrote this in standard form. So let's write the equation of the ellipsoid in standard form. And then graph it. Okay, so our ellipsoid has this equation. Now standard form has a 1 on the right hand side, so to get rid of the 36, we'll divide both sides by 36. That means we divide everything on both sides by 36. 9 goes into 36 4 times, so we get x squared over 4 plus y squared over 4 plus z squared over 36 equals 1. That's standard form. It's helpful though if we write this as a perfect square, that is a perfect square, and that is a perfect square. So we might even go further to say that this is x squared over 2 squared plus y squared over 2 squared plus z squared over 6 squared equals 1. Now it's in standard form. We're not subtracting anything from the x, y, or z, so the center is 0, 0, 0. A is 2, B is 2, and C is 6. Okay, so we're starting at 0, 0, 0. Since there's a 2 under the x squared, so I've got a 2 squared under the x squared, I go plus and minus 2 units from 0, 0, 0 in the x direction. Those points are on my ellipsoid. And since there's a 2 under the y squared, I go plus and minus 2 units in the y direction. And those points are on my ellipsoid. Look what we've got in the xy plane. There's a circle of radius 2 that's making me think of polar coordinates. Okay. And then since there is a 6 squared under the z, we're going to go plus and minus 6 units from 0, 0, 0 in the z direction. And this is not to scale. I'll just call that 6 and that negative 6. It should be over there to that side. Sorry, looks a little Not quite right. All right, so that's my sort of egg shape. Now the projection onto the xy plane, we can see it's right there. That's that circle of radius 2. Now if we didn't see that, if we weren't sure what it looked like, we might say, look at our picture and say, okay, the widest part is where z is equal to 0. So set z equal to 0, and what do you get? You get x squared plus y squared equals 4 if you multiply both sides by 4. So there's your equation of the circle of radius 2. So we sketched our solid. Q is the interior of that egg shape. And now we want to sketch the region R. Now I notice that my region R is a circle. So rather than describing this in rectangular coordinates, and I could, y would go from a negative square root of 4 minus x squared to a positive square root of 4 minus x squared, and x would go from negative 2 to 2. That's an option. I'm going to skip that option. I'm going to say, let's go to polar coordinates. Because in polar coordinates, r equals 0 is here, r equals, I don't know, 1/2 is there, r equals 1 is there, r equals 1.5 is there, r equals 2 is there. So there are these circles, they're sort of radiating out from the origin. They start at a single point and then they go out. They go out to 2. They go from 0 out to 2. And that's what we have right here. So r goes from 0 to 2. It's really hard to do that on a camera. It's much easier to show people in class. I show them these gestures and they're like, yeah, and everybody shakes their head. I don't know if it comes across on camera. If it doesn't, I'm sorry. The r goes from 0 to 2, and theta goes from 0 to 2 pi, so that we get the whole circle. Okay, so those will be our bounds for r and theta. Now in order to get our bounds for z, we need z to go from a bottom function to a top function, which I think we can see right now. It's the top, or the bottom half of this ellipsoid to the top half of this ellipsoid. In order to find those functions, we'll take the equation of the ellipsoid and we'll solve it for z. So we have z equals, or 9x squared plus 9y squared plus z squared equals 36. And I'm trying to get z by itself. So I will subtract 9x squared and 9y squared from both sides. And don't forget to take the square root. In order to get rid of that perfect square, we'll take the square root of both sides. So I'm doing the square root of this equals the square root of that, and a plus or minus on the side that doesn't involve the z. So z equals plus or minus the square root of 36 minus 9x squared minus 9y squared. And I could factor out that 9. I think that'd be a good idea. Because look what happens when I do. I see an x squared plus y squared in there. It's a very good thing for our substitution. Okay, so this is z. This is another way to represent that ellipsoid. And we actually get two functions for z, not one. That's why that plus or minus is so important. Z goes from negative values, so the negative square root, that's the bottom, down here z is negative, to the positive square root, that's the top half of my ellipsoid. So the bounds for z, just in terms of x and y, are these. We go from the negative square root of 36 minus 9 times the quantity x squared plus y squared to the positive square root of 36 minus 9 times the quantity x squared plus y squared. Now, if this was it, if I was in rectangular coordinates, I could stop here and I could use those as my bounds, my lower bound and my upper bound for z. But we want to go to cylindrical coordinates because we looked at that projection of, onto the xy plane and we saw it was a circle. So I don't want to leave this in terms of x and y. So we find bounds for z, initially in terms of x and y, but eventually in terms of r and theta, if we decide that we want to go to cylindrical coordinates. And we do because the projection onto the xy plane is a circle. We also see we've got symmetry about a line, that line being the z-axis. Excuse me. So I replace x with r cosine theta. I replace y with r sine theta. But remember, that simplifies. If I take x squared and y squared and add them together, that's going to simplify to r squared. So we've got that and that. Those are our bounds for z. Those are our bounds for r and theta. Z goes from a function of r to a function of r, so we have to integrate with respect to z before we integrate with respect to r. Since these are constant, the order doesn't matter. Okay, so now I think we have everything that we need to set up our volume integral. Okay. So the volume of the ellipsoid is the triple integral over q of dv. We said theta goes from 0 to 2 pi, r goes from 0 to 2, and z goes from a negative square root of 36 minus 9r squared to a positive square root of 36 minus 9r squared. Now dv, be careful, it's not dz dr d theta, it's dz, and remember dA in polar coordinates is replaced by r dr d theta. So you need, when you're setting up and solving this integral, remember you need two things. You need bounds for z, r, and theta. In terms of z, r, and theta, there should not be any x's or y's anymore. And then you need to replace dv with r times dz dr d theta. And of course you could change the order of that multiplication if you want to. If there was an integrand here, I would write that in terms of z, r, and theta as well. But there's not because we're just finding volume, so the integrand is a 1. We're adding up a bunch of volume pieces to get a total volume. Okay, now we're going to evaluate this. And the way we evaluate the integral is first we start on the inside and we work our way out. We anti-differentiate with respect to z. So we have the integral from 0 to 2 pi of the integral from 0 to 2. The antiderivative of r with respect to z, r is being treated as a constant. So we get a constant times z. And then we substitute our upper bound for z, which is the square root of 36 minus 9 r squared, and our lower bound for z, which is this negative square root of 36 minus 9 r squared. So we anti-differentiated, and now we're going to use the fundamental theorem to evaluate that innermost expression. At the upper bound, actually I'll do it this way. Let's factor out the r. We get the upper bound minus the lower bound, but the lower bound is negative. So we're adding, or we're subtracting a negative, so that means we're adding. So I've got two of those. So I have 2r out here times the square root of 36 minus 9r squared dr d theta. This is an abnormal amount of space. Sorry about that. Okay, and now we look at this integral and we evaluate this. You say, well, how do we evaluate that? We're going to anti-differentiate with respect to r. And this requires a u sub. The function under the radical is our u. I guess first of all I should have said basic rules don't apply because we've got a product here. The next thing I ask myself is, does u sub work? And since I have a function nested inside another function, and a multiple of the derivative of this function is out here somewhere, meaning I'm not worried about the constants, but the r part is out there, then the u sub is going to work. So we let u equal this, then compute du. Derivative of 36 is 0. The derivative of negative 9 times r squared is negative 9 times 2 times r to the 1 less power. 2 minus 1 is just 1. dr. And I need a 2r dr, not a negative 18r dr. Well, we can just divide both sides by negative 9, and that would give us exactly what we want. And dividing by negative 9 is the same as multiplying by negative 1/9. So we get 2r dr turns out to be negative 1/9 of du. Okay, so we have chosen u, we computed du, and now we need new bounds. To get your new upper bound and new lower bound, you just replace the upper bound and lower bound from before into your function u. So we're saying r goes from 0 to 2 here. When I write my new integral, I need to say, what does u go from? U goes from what to what? Let's figure out what those are. Well, when r is 2, u is this. 2 squared is 4. 4 times 9 is 36. 36 minus 36 is 0. And when r is 0, u is 36 minus 0, which is 36. Okay, so now we've got our u, we've got our du, we have new bounds. Now we need to write our integral entirely in terms of u. Okay, so we have the integral from 0 to 2 pi of this integral here. Now 2r dr happens to be negative 1/9 of du. And then this is u, and we're taking the square root of u. Remember square roots, how those work. That's an implied 1 and an implied 2, so that's u to the 1/2 power. And our new bounds, we use the upper bound for r to get the upper bound for u, which is 0. And we use the lower bound for r to get the lower bound for u, which is 36. If you want, you can switch those and change that negative 1/9 to a positive 1/9. That's legal. Some people really don't like having that larger number down here. Either way is fine. I think I will switch it. Not for any particular reason other than the fact that I just talked about it. But that's legal. You can switch those as long as you multiply by negative 1. Okay, then we add 1 to the exponent. And then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. And then you evaluate this from 0 to 36. I've been doing all of this and I forgot my d theta. That d theta goes with that integral over here. Pretty much ignoring it, right? I'm just focused on that, but you need to bring that along in order for all of these to be equal. Okay, so we end up with 2 over 27 times 36 to the 3/2. Minus 0 to the 3/2, which is of course just 0. Now 36 to the 3/2 is 36 to the first times the square root of 36, as we've talked about before, because that's 36 to the first times 36 to the 1/2. The 1 plus the 1/2 gives you the 3/2. Anyway, talked about that a lot already this semester, so I'm not going to get into it too much. Just gives me a quick way to calculate that. So I've got 36 times 6 times 2 over 27. Actually, let's write it that way. 9 goes into 36 4 times, 9 goes into 27 3 times, 3 goes into 6 twice. So what do we get? Is that 4 times 4 is 16? So we have 16, and the antiderivative of constant with respect to theta is that constant times theta. We evaluate from 0 to 2 pi. So we get 16 times 2 pi, which is 32 pi. Okay, so we wrote the integral in terms of u, we anti-differentiated, then we evaluated f of b minus f of a, and then we anti-differentiate with respect to theta, and then we substitute in the bounds for theta. So we do f of 2 pi minus f of 0, and we got 32 pi. You're saying to yourself, what is that? Remember, it's volume. It's volume. That's what this video was about finding the volume of an ellipsoid in cylindrical coordinates, using cylindrical coordinates. So we have this ellipsoid. 32 pi. Is that right? I don't know. I don't know if that's right. I feel like I made a mistake somewhere. All right. So we wrote the equation of the ellipsoid in standard form. We graphed it. We sketched a projection onto the xy plane, and we got this. And then over here, we found the bounds for z. So z goes from this function to this function, and we just found those functions by solving the equation for the ellipsoid for z. And then we wrote those in terms of r and theta by replacing x squared plus y squared with r squared. Once we did that, we set up our integral. We said z goes from this function to this function, r goes from here to here, and theta goes from here to here. And this is where you have to be really careful. A lot of people miss this part. dv is not dz dr d theta. dv is dz times dA in polar coordinates, which is r dr d theta. So we did that. Integrate with respect to z, use the fundamental theorem. Integrate with respect to r, which required a u substitution. Eventually, we use the fundamental theorem. Then we anti-differentiate with respect to theta and use the fundamental theorem to get our final answer. And that's our final answer. I'm not 100% sure about it, though. I feel like I made a mistake somewhere. Maybe not. Maybe it's fine. But that is the volume of our ellipsoid in using cylindrical coordinates. Now, in the next video, we'll do another example using cylindrical coordinates, and then we'll talk about another coordinate system, a very convenient coordinate system for regions that have symmetry about a point. We have symmetry about a point instead of a line. Well, symmetry about a point leads to spheres, so we'll go to something called spherical coordinates.